Yeah, thanks, Shrikant, for the opportunity. I'm happy to be part of this wonderful event. So before I start on my topic, would like to give a brief introduction to Aprecomm. We started Aprecomm by 2016, and we have been providing AI solutions to various verticals of the Wi-Fi industry, predominantly to ISPs and public Wi-Fi and SMB and enterprise segments. So our solution basically helps the customers to autonomously monitor and manage their Wi-Fi networks. So being said that, let me get into the topic in hand, how important role AI can play in this Wi-Fi networks. Um, Today, Wi-Fi is no more a network confined to one place. It is almost available everywhere in your home, in the places you visit, the food markets, retail shops, or the places you go for work, obviously your offices. And we want this Wi-Fi network to come to us rather we following the network. Thanks to the initiatives like the open roaming, public Wi-Fi, it is becoming a reality today that the network Wi-Fi network is available everywhere we go. And this in turn tells us that growing Wi-Fi demands are growing in an exponential way, and this pandemic in fact has accelerated this growth. So with this demand, increasing demand, we see the bigger challenge with the Wi-Fi networks is to see how we will be able to manage it and to provide a very reliable connectivity to the end user. So, so the whole idea of my presentation today is to see how AI can help to achieve this, to manage these Wi-Fi networks autonomously and help you to achieve more reliable Wi-Fi services. So when you say AI, the immediate thing that comes to our mind is resolving complex problems like autonomous driving or places which involves large data like election campaigns or face recognitions and stuff. But when it comes to applying AI on networks like Wi-Fi, there is still a lot of ambiguity around this. Some of the major claims where they say that these AI algorithms are not quite really required, as these existing Wi-Fi algorithms are already doing a great job. AI is just doing the same thing in a complicated way, and it is consuming more resources. These are the claims which we used to, these are the concerns we used to get when we go and present our solution to most of the customers, right? And there are also the most common statement we used to see is AI is very good for analytics. It gives you a bigger picture of what's happening in the network. But when it comes to controlling the network, it becomes unpredictable, and it is hard to say when the system is going to fail. So a lot of the vendors are still reluctant when we go and say, okay, we have an AI system which can control your networks autonomously, right? And another bigger challenge we see is that there is a lot of disbelief that still we don't, still we are not in the place where this network could operate autonomously. So the reason being said is that at some point of time, this networks becomes unpredictable, or the actions done may not be comprehended by the end user. So keeping these ambiguities one side of how applying AI into this Wi-Fi networks, we still see there are a lot of problems which is not just claimed by us, but it is claimed by the industry, bigger OEMs and device manufacturers today. So if you see that in your home networks, at least 10% of the Wi-Fi users face a problem once in a week. This is the data which we get for most of the ISPs. In fact, most of the ISPs whom we have approached, they have agreed that 60% of their problems are complaints which comes from the end users or Wi-Fi issues. So they actually, the users are not going to complain the problem as Wi-Fi. They will be complaining it is an internet problem. But eventually, when they send an engineer, they figure out that the placement of Wi-Fi or interference around the environment is really causing these issues. And there is no proper monitoring tools today to really understand the last mile connectivity of Wi-Fi, whether it is really providing a good experience to the end user. So other major issue is that most of the time, 52% of the time is spent, close to an hour is spent to really understand Wi-Fi problem, because the network as such is more random and complex. There are a lot of variables which needs to be understood to really identify the problem. And in case of enterprise networks, if you see 60%, 64% of the problems are mostly related to Wi-Fi. So what are the actual challenges in this Wi-Fi today? So with the introduction to 11AG, the biggest challenge is to have a bandwidth equivalent to wired networks. From the point of time, the standard bodies mostly focused on improving speeds, filling the gaps between wired and Wi-Fi networks. And today we have completely replaced wired networks, and Wi-Fi is able to achieve multi-gig speeds. So even with these greater speeds, we still have some underlying problems with the Wi-Fi networks. We still need algorithms like ATFs or better RU scheduling algorithms to meet the demands of the user. The next bigger problem we see is that we still need better algorithms to manage Wi-Fi network, selecting our channel or power. And most importantly, a very basic issue we see with Wi-Fi networks today is connectivity, which is a very basic requirement of any network. And still we have a lot of ways to improve the connectivity in a deployed environment, and still vendors are putting efforts to improve roaming and steering algorithms. The basic problem with all these challenges is that we don't have a standard way to handle these problems. In fact, we cannot have a standard way to handle this problem because the network as such is quite random. And so any algorithm which is going to perform well in these networks should factor in this randomness. So you cannot standardize a random behavior of the network. So let's see how today's algorithm actually factor in some of these parameters and how well they are really working in the field. If you take any standard algorithms today, they look on predetermined variables like we have roaming thresholds, or we look for a certain level of congestion to be present in the network, and then consider parameters like rate, RSS, and stuff. So based on these predetermined threshold, we take action. So let's say if the congestion more than 80%, then I want to change the channel. So let's take the same example of channel selection algorithm today. So let's say the algorithm has decided to move the channel because the current channel is congested, and it has looked into the various channels interferences, and then it has figured out that channel 36 and 48 is available for it to choose. But both at that point of time, both channel 36 and 48 is not having any congestion. You can choose either one of them. But if you really want to understand the randomness happening in the environment, channel 48 might have a random interference if you look at the historical performance of this channel. So if you consider that, probably you will choose channel 36 rather than 48. So now let's consider one more variable. Let's say that there are clients in the environment which is not supporting channel 36. Okay, so typically 36 is always supported, but I'm just for a hypothetical sense, I'm saying that there are clients which is not supporting channel 36. Then probably choosing 48 is a better decision. So the decision totally depends on how considering the random behavior of the deployed environment. So it is not just going to be based on some threshold. So today's algorithms, it is not possible to consider all the randomness until you apply a system wherein like apply models based on ML. It is very hard to consider all these parameters with a set of if and else loops. So the basic disadvantage of these algorithms are they are limited to the lab test cases. and they fail when they don't consider this randomness happening in the environment. And it is also not possible to consider all type of randomness which can happen in Wi-Fi networks. And it also needs a way to manually tune based on the changes in the environment. Suppose you have kept a threshold of, let's say, I want to kick a client at minus 75 dBm when it roams from AP1 to AP2. And there was a change in environment where there was some obstruction between this path, and then now you want to change the threshold. Most of these today's algorithms needs a manual intervention from either from the administrator or the service provider to tune the parameters to adapt to the environment changes. So there are a lot of bugs happens with these algorithms because they fail to adapt to environmental changes, and it requires a longer implementation cycle to get the feedback from the field. So after getting the feedbacks and then changing the algorithm, and after redeploying into the field, there are still cases where the problem can resurface. So these are typically problems we have been faced with enterprise networks, and today even home or any SMB networks demands these kind of the randomness in these networks is also as equivalent as enterprise networks. Today in any home, typically we are connecting 20 to 30 devices, and SMBs are like becoming as enterprise where we are having more devices. So most of the deployments are today becoming as equivalent to high density deployments. So a good algorithm is the one which has to consider these randomness and adapt to these problems. So I want to show a simple example. Let's case a very simple case of a roaming algorithm. Let's understand what kind of random variables are present in such an while considering we actually consider designing such algorithms. So, so the first thing is to consider the deterministic parameters like rate, RSSI channel, understanding the application demands. So if you want to move a client from AP1 to AP2, we need to really see whether what is the right point at which we have to either kick the client or initiate certain methods to actually make this client to move from A to B, right? So we first consider some of the deterministic parameters like R rate, RSSI, understand the application demands, and also try to understand whether the network is as such good. And then if you see, to make a decision, there are a lot of other factors which influences the decision. Suppose if you are trying to kick a client at minus 75 dBm, but the client actually disconnects at minus 75 dBm. So it is so clicking in such a client will actually result into roaming failure than a smooth roaming experience. So there are cases where we have seen that when the congestion on the current AP is above 60%, the client disconnects at very lower, like minus 70 dBm itself. Whereas in a typical case, you would have considered that the client will be still connected to still minus 80 dBm, and you would have tuned your thresholds to keep the client at minus 75 dBm. So the way these client behaves actually influences your algorithm. So you need to understand how the behavior of the client as such, and this behavior of client varies from client to client depending on how these clients have implemented the algorithm. So to one static threshold will never work in ensuring that you will have a smooth roaming experience. There will be always failures, and if the deployment has more such randomness, the failures are going to be much higher. So what we do as a part of our AI models is to consider this randomness in the environment and then adapt to this random behavior. So I would like to show you one of our setup where we actually compared a standard algorithm with our AI algorithm. So this is the setup we use to tune our AI models. So typically the setup has office and conference room, and people tend to move from the office and conference room, which is quite common in many office scenarios. And we have a small lab between these networks. So this is the lab where we will try to introduce some kind of randomness to test our algorithms. So what we typically do is initially we set up the AP such a way that the roaming is quite smooth between these office and the conference room. You can see that when the client moves from from the office to conference room, it was initially at minus 45 dBm, and slowly the signal degrades, and at minus 75 we do a kick threshold is programmed at minus 75. So we kick it at we kick the client at minus 75, and it smoothly roams to the next AP, and we have a better signal. So 95% of the time we used to succeed in an environment like this. But when a sudden change happens in the environment, so what we usually do is we put a whiteboard which has a metal sheet behind it, so which will attenuate the signal. So the signal attenuation happens in the path. Now the thresholds are going to vary, right? So the point where you see minus 55, it becomes minus 65 dBm, and since your peak threshold is at minus 75, even before that, the attenuation happens at a much higher rate, and the client tends to disconnect and fails to roam. And so when we introduce an abstraction like this, we see that the failure rates are so high, almost 70% of the time it failed to roam. So the same setup we try to do with our algorithm. So initially, our AI algorithms also kind of used higher thresholds, peak thresholds at minus 78 dBm. And when we introduced the abstraction, we see that the algorithm sees there are failures happening, and it is also similar to what the standard algorithm sees today. But as it sees the failure, it starts adjusting the thresholds, and then finally settles down at minus 63 dBm, and we see that the roaming becomes smooth again. So in this case, what really does happen is, since we are kicking the clients a little earlier, because we see that most of the time after 65 dBm the clients are failing to connect. So the algorithm slowly moved the threshold towards minus 63 dBm, and which has improved the roaming experience largely. So this kind of adaptation to randomness in the environment is what AI algorithms can bring in. And we see that with more and more demand increasing, and more and more the environment is becoming very dynamic with heterogeneous client setups, it is important to bring AI-based intelligence to your networks. So being said that, a good AI model is all about how well you design the data, right? So with the years of experience of data and designing various models, we have seen better results. We can get better results by combining deterministic and stochastic models. So stochastic models introduce some level of randomness to your decision. So it is always better to have some kind of variations to your decision, so that it converges to more precise decisions when the randomness of the environment is quite high. So the biggest challenge is to get the right data for your AI models from the field, so that you can take better decisions. So we've seen that there are 5 major factors you need to consider when you design your data model. One is identifiers, then the classifiers, behavior, which actually consider the behavior of the client, and the parameters which impact your decisions, and obviously the service level assurities which you require to make the decision. So let me go through one by one what actually I mean by these data points. So identifiers are the key indicators. So let's say you are trying to design a data model for steering algorithm. So probably you need to understand whether the client is having capability like 11B or 11R, and if it is having those capabilities, you make your decisions to keep the clients needs to be a little different than when comparing the clients which is not having 11B or 11R. So you need a very good domain knowledge to understand the key identifiers before you design your algorithms. And the next comes is the classifier, which actually scopes the frequency of the problem or the randomness in this environment. So let's say you want to understand a client failed to get a DHCP IP, and you want to understand why this is happening. So DHCP, the first thing you would like to understand is this DHCP IP issue is happening only with this client, or it is happening across your network, or it is specific to the AP. So how frequently this is happening. Let's say 1 out of 10 times this is happening, and then the factor of entropy is going to be smaller. But if it is always happening, and the factor of entropy is going to be 1, which tells us that there is no much randomness, and this issue is always happening, and it is pertaining to the client and not to the whole network. So these classifiers kinds of give you an input to understand whether to understand the scope of the problem. And then comes the very key parameter we call as a behavior. So behavior defines, once you take a decision, how well the particular the decision is going to resolve the issue which is currently in hand. For example, if there are, let's say you want to move the client from a 5 GHz band to 2.4 GHz band, and and you also understood there is an application demand, and the client is demanding somewhere around 20 to 30 Mbps of bandwidth. So when you want to move this client, you also need to understand whether the client has an affinity to 2.4, because when you go and pick the client, there is a possibility that client will fail to roam or fail to steer to 2.4. So these kind of behavior of the clients needs to be known upfront. So this can be understood by seeing the historical behavior of the clients in the network, and we kind of constantly needs to record that, and then profile the behavior of each of these clients. So this is one of the data points for your models. And finally, the impact, how good your change is going to be. So when you make the change, when you decide to steer the client, is it going to give an improvement of bandwidth by 10 Mbps or more? Is it actually going to satisfy the demands of the application? So this is very important, because you don't want to take a decision where you don't see a really taking this decision is really going to help the client to meet the demands. So until you meet the demands at least by 50% or more, you don't need to take the decision. The last most important data point is the SLA. Let's say you want to improve your connection times. Currently, the client is taking 2 seconds to connect, and by just changing certain parameters or power levels in your AP, you are trying to see the clients are going to connect a little faster than what it is today, right? Or by introducing another AP in the environment, will it is going to help or not. So you need to see whether your SLAs is going to largely improve by taking the decision. So these are the major data points we need to consider when you want to design a data model.
Guhan?
Yeah.
Can we wrap it up quickly so that we are close to your end time?
Okay. So let me just quickly go over some of the data points we used to consider when we design an algorithm, when steering algorithm. So if you see that in case of identifiers, we used to consider about the client model's capabilities, and in case of classifiers, we try to we try to understand the randomness in the path. So it is typically these are the parameters which we require in order to design a good AI model. So I'd like to show some of the algorithms we have today and how they are really helping one of our customer deployments. So you can see that this is one of the our office deployment where the customer has initially had issues with roaming, and they've seen most of the clients' average rates were very low. And once we have deployed our model, we have seen that so we have an algorithm called ICA, which basically adapts the power of the AP and tries to minimize the overlaps or increase the overlaps depending on the environment. So with this, we see that average RSSI and rates of most of the clients in the deployment has greatly improved. Similarly, we have an ICS algorithm. So this is one of the paths in the customer setup where we have seen that when the clients are moving from A to B, they are actually disconnecting and then connecting. And if a customer is using video streaming application, so they have a very poor experience. So with ICS, we do see that the clients disconnect, but so this ICS is being programmed to change the threshold depending on the behavior of each client. So you can see that some of the clients are doing this, in fact disconnecting, but they are immediately connecting, ensuring that there is a good experience when you have streaming applications like video. So another important point for your data model is to consider a feedback system. So even though you have designed your AI algorithms, this is still bound to fail in certain cases. You will not be able to consider all that kind of randomness which is happening in the network. So one way to get the feedback is manually from the field. So the customer complains that he has an experience issue, and then you go and analyze the data and then probably find a solution for it, and then feed that information back to a training model to train the data. Another way is, and this way obviously requires a lot of time and effort. Other way is to design a root cause analysis model using an AI algorithm, which automatically measures the user experience and scopes the problem and correlates the data and then provides the inference where it is failing. So this in fact, we have developed a similar model which can collect all the metadata. So the one which measures the user experience, we call it as Hisense, so which actually measures the experience. So this is one of our dashboard views. Let me just quickly go over due to the lack of time. So we also have a correlation model which provides the output. So the biggest challenge for you is, after developing all these modules, is to ensure the customer believes that the AI is making the right decision. So you need to give, we need to provide a way to visualize the data the AI model has considered in order to make these decisions. So we also have a very good visualization dashboard which tells you why we have taken a decision. So finally, the most important factor is most of these algorithms has to take decisions in real time. So you cannot send all the data back to the cloud. So we have divided our intelligence into two parts: the edge and the cloud intelligence. So within the edge, we also have a way to store and profile client behaviors. We call it as a Cortex 2. And on the distributed intelligence, on the cloud side, we take decisions where we have to correlate bigger data across deployments to take decisions like which firmware is working well or not. So as
yeah, can we close it so that
I think I'm almost done. So
okay, thanks, Guhan.
Yeah.
So there are a couple of questions, so I thought we'll give some time for questions. So there's a question from Stanley, I think which you have partly answered. Is the AI residing in the AP or on the cloud controller? If it is in the AP, how about AP to AP coordination?
Yeah, so our intelligence, as I told you, it is distributed in two parts. So wherever we want to take immediate decisions, the intelligence resides in the AP, and we also have an inter-AP communication protocol. So where we coordinate the movements of the clients between the APs and take the decisions.
Okay. Anurag Kumar has this question: including randomness and adaptation in a model does not make it AI. Classifiers require training from a lot of data for the same or similar situation like the one shown in your example. But scenarios vary so much even for movement within a building, people, building material, etc. How do you train your model?
Yeah, so that's a very good question. In fact, so first thing is to have very good domain knowledge on what parameters you need to consider, right? As he says, there are a lot of randomness in a building. We cannot consider everything. So we do have emulators, and we kind of create various models like airport network, or you want to create a mall kind of setup. So we try to simulate these data. That is one way. And today now we have more deployments in the field. So we also have field data to train our models. Obviously, as I told you, whatever the training we do, they are prone to failures. And so we also have an RCA algorithm, root cause analysis algorithm, which kinds of collects the metadata required for our training. So it is a continuous process, maturing the model. And we constantly train and mature these models and redeploy them to get better results.
Thank you. I have one last question from my side before we close. So do you have any requirements on the AP side to kind of bring in your AI solution? Do you play with all kinds of APs, or do you have certain requirements on the AP side?
So on the AP side, we don't need much bandwidth. So most of the APs we use CPU from somewhere from 10 to 15%. So there should be a window of 10 to 50% CPU required, and our memory usage is somewhere between 8 to 20 MB, depending on the various features we enable.
Thank you, Guhan. We also would like to thank Guhan and his team from Aprecomm. Aprecomm are sponsors for Wi-Fi KS, and I hope this information is useful for all of you.